Hi everyone, I'm Yantiing. This is a video that provides an introduction of our work on certifiably robust FCert classification with foundation models. It's a joint work with Wei and Jinyuan. Traditional supervised learning needs a lot of label data. They could be expensive or even impractical in many real-world applications. Nowadays, many tech companies all release their foundation models. In the image domain, we have Dino and Clip as two well-known foundation models, and in the text domain, we got POMTIL API and OpenAI API that provides text embeddings as cloud services. Using their high-quality embeddings, anyone can build accurate downstream classifiers with only a few training samples, leveraging techniques such as linear probing and KNN. Suppose a user wanted to classify cat and dog images. The user could collect a few training samples, which are also called support samples for each class, from the internet. Then, the user could use the foundation model to extract features for these support samples, and subsequently train a linear classifier on these features. Given a testing input, the user also uses the foundation model to get its feature, and then its label could be determined using the classification boundary. However, FCert learning with foundation models is vulnerable to data poisoning attacks. The attacker is able to misclassify this testing input by poisoning only one support sample. Specifically, the attacker could poison one cat image such that its feature collides with that of the testing input. Then, to minimize the training loss, the classification boundary is shifted, and the testing input is misclassified as cat. It's worth noting that it's very hard to manually inspect the support set. This is because the perturbation made to the poison image could be invisible in human eye. Existing defenses against data poisoning attacks could be classified into empirical defenses and certified defenses. Empirical defenses cannot provide formal robustness guarantee, so they may be compromised by adaptive attacks. On the other hand, certified defenses provide a performance lower bound under arbitrary attack once the number of poison support samples is bounded. Existing certified defenses, such as bagging, DPA, and KNN, are designed for traditional supervised learning, so they have suboptimal provable robustness guarantee in the FCert setting. The reason is that, by design, these defenses do not consider the high-quality features provided by foundation models. Next, we introduce our FCert, a certified defense for data poisoning attacks that is specifically designed for FCert learning. Our method calculates a robust distance for each class. We first calculate a feature vector distance between the test input and each support sample in a class. Then we remove a certain number of largest or smallest feature vector distances and takes an average over the remaining feature vector distances as the robust distance for this class. Lastly, we predict the class with the smallest robust distance. The intuition of our design is that these robust distances are insensitive to the changes of the support samples. Therefore, the final predicted label is also stable under data poisoning attacks. Here we provide a concrete example for FCert. In this example, there are 3 support samples in each class, and the attacker is able to poison one support sample from each class. Our method first uses the foundation model to extract feature vectors for all support samples. The attacker manipulates the cat image such that its feature collides with that of dog images, and vice versa for dog image. Our method calculates the feature vector distance between the test input and each support sample. And then our method orders these distances for each class separately. And then we remove the smallest and the largest distance for each class. and the remaining distance is considered as a robust distance. We can see that in this step, the distances calculated from poisoned spore samples are removed. And lastly, we can see that the robust distance of the dog class is smaller than that of the cat class. So dog is the predicted label after data poisoning. Next, we use this example to illustrate the provable robustness of FCert. Suppose that before attack, the distances of the 3 cat images to the dog image are 4, 5, and 6, and the feature vector distances of the 3 dog images to the testing input are 1, 2, and 3. To minimize the robust distance for the cat class, the best strategy of the attacker is to change the cat image with the largest distance to become the smallest. The new robust distance after this attack is 4, and that is the robust distance lower bound for the cat class. And likewise, to maximize the robust distance for the dog class, the attacker changes the dog image with the smallest feature vector distance to become the largest. The new robust distance for the dog class is 3, and that is the robust distance upper bound for the dog class, which is smaller than the robust distance lower bound for cat class. So for this testing input, so our method provably guaranteed to predict for the same label after the attack. For experimental setup, we consider 2 threat models. We consider individual attack where the attacker can poison T spore samples in each class. And we also consider group attack where the attacker can poison T spore samples in total across all classes. We use Dino V2 as the foundation model and use tiered ImageNet as the dataset. We compare with both the empirical method and the certified defenses. We also consider many other settings. Please refer to our paper for more details. Our experimental result shows that our method outperforms existing baselines in general. Our method has a greater advantage when the number of poison spore samples becomes large. And that would conclude this video, and thank you for your attention.